In this video, we're going to discuss why reactions happen and look at a case study, which is the energetics of the keto-enol tautomerization. So our goals are to describe some of the factors that affect whether or not a given elementary step occurs, to explain with bond strengths why most carbonyl compounds favor the keto tautomer at equilibrium. You may have no idea what I'm talking about. That's cool. We're going to get there. And then provide the structure for the enol or keto tautomer of a given molecule. And then finally, draw the complete curved arrow mechanisms for the tautomerization of enols to ketones and vice versa in both aqueous, acidic, and basic conditions. So clearly there's a few words here that we probably need to make sure that we get. So tautomerization and tautomer, that's one of them. I haven't heard that word before. Keto, you might know, but enol, I haven't heard about that before. Okay. So we're going to review and recap the 8 elementary steps that we learned in our previous video. Also, there's also proton transfer and carbocation rearrangements that are not listed here. Of course, we know proton transfer. You have a Bronsted-Lowry acid and a Bronsted-Lowry base. The Bronsted base accepts the proton. The Bronsted acid donates it, generating the conjugate base and then the conjugate acid of base B. A carbocation rearrangement, an example of that, well, maybe, let's say you have a carbocation like this. It undergoes some hydride shift to make a more stable carbocation, so secondary to tertiary. So excluding those 2 types of steps in the reactions of organic compounds, we want to think about these other 8 steps. So go ahead and see if you remember what each of these were, if you can describe the pattern represented by each of these 8 steps. Last chance to pause. Okay. So we're going to look at each of these steps one by one. I'm thinking about the bimolecular nucleophilic substitution. We have some nucleophile, an electron-rich species, using its electrons, so its non-bonding pair of electrons, to attack sigma star CX, or in this case, X is bromine. It doesn't have to be. And when you fill that sigma star bond, you break the bond. And so you end up cleaving this bond, and you have a bromide leaving group. And then you have what we call the substitution product. You have this new sigma bond. And as you might expect, the strength of that sigma bond and the stability of the leaving group versus the stability of the nucleophile is going to determine whether or not this step takes place. Okay, let's look at a bimolecular elimination. So an E2 reaction. So an E2 involves a strong base, and that strong base is going to attack sigma star CH. So sigma star CH. And then this one was pretty tricky, right? Because then the electron, so you fill sigma star, and that breaks sigma. So fill sigma star, that breaks sigma CH. And then where do those electrons go? Where do the electrons go that are in that bond? Well, they're going to go and make a pi bond here. They're going to make that pi bond. And they do that, let's pick a good color. They do that by overlapping with sigma star CBr. Here it is again, showing up twice in a row here. Okay, so that's described right here. So we have sigma CH overlapping with sigma star CBr. You fill up an antibonding orbital and you're going to break a bond. So you break sigma CBr. And then that generates a lone pair on the leaving group, and you made a pi bond here. Now, of course, the stability of the leaving group, that's going to determine whether or not this reaction takes place, for example, as well as other factors. Okay. Good. So let's look at coordination and heterolysis. So coordination, we have a Lewis acid. It has an empty orbital. It can accept electrons. So the carbon here is sp2 hybridized. It has an empty p orbital. And that empty p orbital, which actually is coming in and out of the plane of the board. So we'll just imagine that we're looking on top of that p orbital. So we have a bird's eye view of a p orbital here. And then that non-bonding pair of electrons on bromide, attacks it. And all it does is it makes a bond. You just had a filled orbital and an empty orbital, and they're just going to make a bond. All right, that's coordination. And I think it makes sense why this might occur. I mean, you've filled up an empty orbital, so now everything, all the atoms obey the octet rule. We made a bond. That's great. Heterolysis, however, is the reverse of coordination, and so we simply break a bond. And I think for this one, you might wonder, like, how does this happen? Well, I mean, it just does. The bonds, and it's more complicated than that, right? But it can. I think that's the better answer. So the bond can just cleave, and it can form the Lewis acid, the carbocation, and it can form, this time we call it the leaving group. Of course, it was the Lewis base for the coordination. And if you wonder whether or not this is going to happen, if it's going to be favorable, I mean, obviously this is going to depend on the stabilities of these species. That will determine whether or not this heterolysis will occur. But of course it can. This bond is always vibrating, and it can vibrate so much it breaks. Okay, electrophilic addition. So we have an alkene plus an electrophile. So an alkene, our alkene is our electron-rich species. It'll be our nucleophile. And then the electrophile, this is our electron-poor species. And I've kept it generic here. And then we have these pi cc electrons just making a bond to some empty orbital on the electrophile. So you make a bond. Only one of these two carbons can make a bond. So I've just chosen the one on the right. The one on the left, well, now it has an empty octet or incomplete octet. It only has 6 electrons around it. And we formed an electron-poor species, and I bet this thing continues to react. But we'll worry about that another day. Okay, electrophilic elimination. This is the reverse of electrophilic addition. So you can see we have our starting material is the product of electrophilic addition. And then we can see that all that's happening here is this bond is cleaving. You're making the pi bond, and then you've eliminated the electrophile. So it's left, so leaving group, so elimination. Okay, why would this happen? Well, where is the charge more stable, on carbon or on the electrophile? That's going to depend on what you have and what else is involved in the reaction. Let's go to the next one, nucleophilic addition. So for nucleophilic addition, we're going to have a polar pi bond. The alkene is an example of a non-polar pi bond. Right? Those carbons are the same atom. They have the same electronegativity. So they're the same element. They have the same electronegativity. So this is a non-polar bond. So that we had a non-polar pi bond for electrophilic addition. For nucleophilic addition, we're going to have a polar pi bond. And we're going to see that we have some nucleophiles, so electron-rich species, attracted to that partial positive on the carbon of the polar pi bond. And then if we fill up pi star CO, well, what is that going to do? Well, that breaks pi CO. And those electrons have to go somewhere. They're going to go on oxygen. So here they are on oxygen. Okay, so we've gone from this trigonal planar starting material to what you will see next semester is called a tetrahedral intermediate. Now this carbon that was the carbonyl carbon, it's sp3 hybridized, is tetrahedral. So I'll just go ahead and name that for you right now. Okay, but we can see we have the pi bond is broken. It's gone now. The pi CO is gone. And then we have a new sigma bond formed. Now the opposite of that is nucleophile elimination. So last one, guys, you're almost done listening to me talk. So we have nucleophile elimination as our last step here. And what we see is that one of these lone pairs on oxygen, it comes down, it reforms the pi bond, and it expels some nucleophile, some electron-rich species. Now, why do you think this happens? Well, pi CO is a strong bond. And so that's the driving force for this reaction. There's also an entropic driving force for this step. Certainly, delta S is positive because you've gone from one thing to two things. Okay, so I've given you a lot to think about here. And there's been three main themes. So charge stability, bond strengths, and it's complicated. So I would like for you to think about where we used these three factors to describe what's going on in these 8 elementary steps, because we're excluding proton transfer and carbocation rearrangements just because 8's already a lot. So think about, where did charge stability matter? Where did bond strengths matter? And where was it was complicated? It's hard for me to explain to you why the step occurs. So that's something for you to do on your own. Now we're going to look at a case study. We're going to look at the keto-enol tautomerization. So most ketones are in equilibrium with their enol tautomers via what is called a keto-enol tautomerization. This keto-enol tautomerization can happen under acidic or basic conditions. The ketone I think you're familiar with. You have a carbonyl with 2 alkyl groups bonded to that carbonyl carbon. Okay, so the carbonyl carbon is here. And let's think about what we see happening as we go to the enol. Well, what is the enol? Well, the enol is really similar, except it looks like that one of these hydrogens on what's called the alpha carbon, so the alpha carbon is adjacent to the carbonyl carbon. And you can see that this molecule has 2 equivalent alpha carbons because you have 2 methyl groups. They're exactly the same. So one of the hydrogens on that methyl carbon, on the methyl group, on the alpha carbon, it has actually moved to the oxygen. So tautomers are constitutional isomers that are in equilibrium with one another. Excellent. So where does the name enol come from? Well, ene, that would be the alkene. And ol, well, that's the alcohol. Okay, so we have a ketone in equilibrium with its tautomer, the enol. And these are called tautomers because they are constitutional isomers. So we'll think about the curved arrow mechanism for how these 2 molecules interconvert in a little bit, but it can happen in acidic conditions or in basic conditions. So when you have some proton source, and we'll just look at aqueous conditions, so in water, or when you have some base in water. So can you predict which is more stable, or which is favored at equilibrium, the ketone or the enol? So go ahead and make a prediction now. What is favored at equilibrium, the ketone or the enol? Well, you have an equilibrium constant greater than 1 or less than 1. All right, so it turns out that the ketone tautomer is heavily, heavily, heavily favored at equilibrium. For most ketones, not all, but for most, there's greater than 99.99% of the ketone form at equilibrium in contrast to the enol constitutional isomer. Even though they're in equilibrium, and I'll show you how they can interconvert, it's quite simple. So how can we think about this? That maybe isn't so simple, huh? Let's think about what bonds are different between the ketone and the enol. Like think about our list of factors here. So charge stability. Well, the ketone is not charged and the enol is not charged. That's not going to help us. It's complicated. Well, maybe, but I think it's going to be bond strengths. Let's take a look at that. Let's look at the bonds that are different. So in the ketone, we have a pi CO bond that we do not have in the enol. In the enol, we have a pi CC bond that we do not have in the ketone. What else? Well, we have a sigma CH bond. So one of these sigma CHs here, this sigma CH bond, it is not in the enol. It's gone. It's now an OH bond. So we have the CO pi bond versus the CC pi bond, and the CH sigma bond versus the OH sigma bond. We're going to investigate the different bond strengths for these bonds. So the bond strength of pi CO is 720 kilojoules per mole. For sigma CH, we have 440 kilojoules per mole. And for the ketone, we have a grand total of 1,160 kilojoules per mole. Let's take a look for the enol form. For the enol form, we have I'm getting ahead of myself. For the pi CC, we have 620 kilojoules per mole. Okay, so you can see it's a weaker bond than the pi CO with a higher bond strength. Takes more energy to break pi CO. And then for the OH sigma bond, we have 500 kilojoules per mole. So this is slightly stronger than a sigma CH. And then we can see we have a total of 1,120 kilojoules per mole bond strength for those bonds that are different in the enol versus the ketone. So now when we take the difference here, the difference in energy between these two tautomers is 40 kilojoules per mole. And this is a pretty huge difference in energy. And so it results in this equilibrium constant being quite large, much greater than 1. And so where we have, in most cases, for most ketones, greater than 99.99% ketone and just trace amounts of the enol. And this primarily has to do with how much stronger a pi CO bond is compared to a pi CC. All right, now that we can think about why the ketone form is favored relative to the enol form, we can try to propose the mechanism for the keto-enol tautomerization. We're going to try under acidic conditions first. So we're going to be under aqueous conditions. So we have water, then we have some trace acid, some catalytic acid. So catalytic just means that the acid is not consumed in the reaction. It will be regenerated at the end of the process. All right, let's think about what we need to do here. We need to make the OH bond, the OH sigma bond. We need to break one of these sigma CH bonds. We need to break the pi bond, and we need to make the pi CC bond. So what do you think we're going to do first? Are we going to break the sigma CH, or are we going to make the OH bond? Well, we're in acid. And when you're in acid, you're going to protonate something. At least when you're in strong acid, that's what we're going to do. We're going to protonate something. So if we have HCl in water, immediately a Bronsted-Lowry acid-base reaction will occur where hydrochloric acid will donate its proton to water to generate hydronium. Oh, I can't do anything correctly. All right, hydronium here. So we're going to have hydronium in solution. And how do I know? Well, because the pKa of hydronium is -2 and the pKa of HCl is -7. So the equilibrium constant is for this reaction is going to be 10 to the 5. And we're going to have a hydronium, period. It's called the leveling effect. Immediately you put the HCl in and it makes the weaker acid hydronium. The strongest acid you can have in water is hydronium. All right, that was fun. So we have hydronium, and that's going to protonate the ketone. That's going to protonate this electron-rich site, the non-bonding electron pair on the ketone. And if I had asked you what was the highest energy pair of electrons on the ketone, you would have told me that it was the non-bonding pair of electrons on the ketone. Okay, so we're going to end up with a protonated ketone here. Okay, so one more time. So we have our non-bonding pair of electrons on oxygen from the ketone. It is the electron-rich species. It is donating into sigma star OH. For our hydronium, that's our electron-poor species, which we can see from the positive charge on oxygen. And if we want to name the step, this is a proton transfer reaction. All right, awesome. We have the protonated ketone. We have broken, or we have made rather, the OH bond. Check. So what else do we have to do? We need to break the CH, and we need to break the pi and make the pi CC. So we're going to do that all now. We're going to break this sigma CH bond. Now you could ask, well, how exactly are you going to do that? Well, if we're going to deprotonate, so we need a base. What base do we have? Well, water was formed here, right? When you deprotonated hydronium, you formed water, and water is a base under acidic conditions. Whoa, that's confusing, right? But hydronium is the acid and water is its conjugate base. So water will be a base under acidic conditions. So now we're going to have that lone pair on water attack, sigma star CH. And then the electrons in that CH bond, because you fill sigma star, you break sigma. They're going to come and they're going to make that pi CC. Let's write all this out. So that broke, our first step, it broke sigma CH. Now, these electrons, they're going to make the pi CC by essentially donating to pi star CO. That breaks the pi CO bond, and those electrons are going to go to oxygen. We don't have that lone pair shown, but there it is. All right. So there were two main things that needed to happen. We needed to make the OH bond, break the CH bond, and then also, we have the pi CC versus the pi CO. If you're an acid, you're going to protonate something. So we made the OH bond first, and then we deprotonated and made the pi CC. The Keto-Enol Tautomerization can also happen under basic conditions. Now we will propose a curved error mechanism that explains the formation of the enol from the ketone under these conditions. There's a few key things that must happen. We must break the sigma CH between this alpha carbon, the one that's adjacent to the carbonyl carbon, and we must make the OH bond. We must make a pi CC, and we will break a pi CO. Now we are in base. So under basic conditions, what do you think we should do? Yes, we should deprotonate. We should remove a proton. So we're going to break sigma CH first this time. So the base, sodium hydroxide, or hydroxide, because sodium is a spectator ion. It will donate its non-bonding pair of electrons to sigma star CH. When you fill an antibonding orbital, you break the bond. Those electrons in the sigma CH bond, they come and they make the pi CC bond that we see over here. And that breaks the pi CO. So that makes the pi CC. Can't have 5 bonds to carbon, so it breaks the pi CO. And if you draw the products of our arrows, you will get this species and water, the conjugate acid of hydroxide. Now the organic species is called an enolate. It looks a lot like an enol, but instead of the ol, right, we have a negative charge. And so we have that ate ending at the end of the name, enolate. So we've really done most of what we needed to do. We broke the CH bond, we made the pi CC, and we broke the pi CO, and now really all there is to do is to make the OH bond. So we need a proton source, and under basic conditions, water is a proton source. So it is an acid under basic conditions, meaning it reacts with bases. Okay, and so we're going to have now that non-bonding pair of electrons on the oxygen of the enolate reacting with sigma star OH for water, and then those electrons, so you fill an antibonding orbital that breaks the bond, so it breaks the sigma OH, and then those electrons go to the oxygen and water. And we actually didn't even draw hydroxide here, but those electrons go and you regenerated hydroxide, which is why this is called catalytic. Under acidic conditions, we protonated first. Under basic conditions, we deprotonate first. We use the base. So in basic conditions, you use the base, you deprotonate. In acidic conditions, you use the acid, you protonate. So whenever you're proposing a mechanism, which you're going to be doing more and more of, you just stop and you think, what are you? What's your role? Oh, you're an acid? Cool. I'm gonna protonate something. You're a base? I'm gonna deprotonate something. Or we're gonna take a little bit of a step back and draw the enol now for each of these ketones. So go ahead and pause and try it for yourself. And if there are 2 possible isomers, draw the more stable one, please. So what we need to do here to draw the enol is we need to identify the alpha carbon. We probably need to identify the carbonyl carbon. One of these hydrogens on the alpha carbon will be moving to the carbonyl. You'll have that pi bond between the alpha carbon and what was the carbonyl carbon, and you'll have an OH here. Okay, so let's go ahead and start by identifying alpha carbons. So for this first molecule, it just has 1 alpha carbon. It has this one. That's the CH3 group. So we'll just go ahead and show that. So we're going to deprotonate here. On the other alpha carbon, there are no hydrogen atoms, so you can't make an enol there. Okay, so now we have a CH2, and we've moved this proton from the alpha carbon to the oxygen. The pi bond is moved from between carbon and oxygen to between carbon and carbon. If we move on to the right, we see a molecule that has two equivalent carbons, alpha carbons. Those alpha carbons are exactly the same, just like they were for acetone, which was the prototypical ketone that we have been examining on the previous slides. So we're going to imagine deprotonating one of these alpha carbons and transferring that proton to oxygen, moving the double bond from the alpha carbon to the OH, moving the pi bond from pi CO to pi CC. So we have our enol. If you didn't pause, maybe you want to now. And if you did, maybe you want to pause and just be sure that your answers for these two questions are correct, or you still agree with them, given the examples that I've just shown you. Now for the final examples, they get a little bit trickier. So bottom left, we have two different alpha carbons. I'll distinguish them by alpha and alpha prime. And so we could have two different enols. If we deprotonate alpha, we would get this double bond. If we deprotonate alpha prime, we would observe this enol. So which one do you think it is? Well, it is going to be this one. Enols, think about the ene in enol. We have what looks like a tetrasubstituted alkene versus a disubstituted alkene. So what is more stable? The tetrasubstituted. So I predict that the enol, circled in pink, will be observed. Okay, last molecule. So for this molecule, it actually only has one alpha carbon because it's an aldehyde. And even for the aldehyde, we call this the keto form. It's the form that has the carbonyl, the CO double bond. Well, the nice thing is that we really only have one choice here. We have one alpha carbon. So one of these hydrogens is going to move to oxygen. You make a double bond between the formerly alpha carbon or alpha carbon and the carbonyl carbon, and then you have your pi bond here, CC rather than CO. All right, very good. So make sure that you can draw enols of ketones and that you could do the reverse, that given an enol, you could draw the ketone it came from. All right, let's see if we've achieved our learning goals. Can you describe some factors that affect whether or not a given elementary step occurs? I think that you can. So charge stability. What else did we say? Bond strength. And then we said it's complicated. So, I mean, look, there's just a bunch of factors that we're not going to learn in this class and that you're not going to learn unless you go to graduate school. So it's complicated. It's beyond the scope of this class. But in this class, we'll use charge stability and bond strength to analyze these reactions. And particularly as we move on and learn and zoom in on some of these reactions, we're especially going to think about charge stability. So for example, bromide is more stable than chloride. How do I know that? Well, bromide is a weaker conjugate base, right? Because it comes from a stronger acid. So if a reaction starts with chloride and ends up with bromide, it might be stable because bromide, it's stable. It's more stable than chloride is. So I might predict a reaction to occur that starts out with chloride but ends up with bromide. Okay, so charge stability, bond strength, it's complicated. So let's explain with bond strengths why certain elementary steps occur. And the one that we looked at this time was two elementary steps, so it's two proton transfer reactions, and it's why carbonyl compounds favor the keto tautomer at equilibrium. So we can do that. We want to provide a structure for the enol or ketone tautomer of a given molecule. We just accomplished that goal. And then finally, probably the hardest is to draw those complete curved arrow mechanisms for the keto-enol tautomerization in both aqueous, acidic, and basic conditions. So in acidic conditions, you're going to protonate first. Protonate means make a bond to hydrogen. And in basic conditions, you're going to deprotonate first. And just let that guide you. Okay, time to practice.